Welcome, class. In this video, I wanted to go through a practice problem dealing with the method of initial rates that we use to talk about kinetics, right? To use to determine rate laws based on this kind of experimental data. So a typical problem might be something like this. Right? You're going to have some given data, right, where you're given various trials. So in this case, let's just label these. All right, we have trial 1, trial 2, trial 3, trial 4. And these are you're given the concentrations of the reactants and what the measured rate was from that experiment. Now, in the problem, you're also going to be given typically the overall reaction. And you're likely going to be asked to calculate the rate law. You may be asked to also calculate the rate constant. Okay, so what I want to do is just walk through the process that you would use to do this. Okay. So the first thing to keep in mind is that while we can't write the specific rate law based on the observed equation, what we can do is give an overall sort of format of the rate law, if you will. So the first thing that we can write is that we know the rate law is going to take the form of the rate is going to equal some rate constant times our reactants, the concentration of our reactants, raised to some order, to some exponent here. So while we can't know what the rate constant is or know what the actual orders are just from looking at the overall equation, we can write the form. And this gives us a little bit of an insight on what we need to do to come up with the rate law, right? We need to calculate the orders, right? We need to figure out what the orders are, and then ultimately figure out what the rate constant is. So as we go through the process, the first thing is to figure out what the orders are. Now remember, I'm going to show you two approaches to do this. One is an observational way. So we can often do this without doing any kind of really calculations, if you will. And that is by looking at, if we can tell just by looking at a pair of reactions whether something is zero, first, or second order. So let's go through how we might approach that. So remember, the thing that we need to do is we need to pick two trials where we're only changing one concentration. And so, for example, if I pick trials 1 and 2, I can use that to determine the order with CHCl3 because I change this concentration, but I leave Cl2 alone, right? So this is constant. So what I've done here is I've doubled the concentration. So let's see what the rate response is. So the rate response went from 0.0035 to 0.0069. So what we can look at just by observing this is it's basically doubled as well, right? So doubling would be 0.007. So essentially, this has also gone up by twice. So if we see a mirrored response, if we see the same change in the rate as we did in the concentration, then what does that tell us? Well, it tells us that it's first order. In CHCl3. Now we can do the same thing with Cl2. We find two trials where the Cl2 concentration has changed, but the CHCl3 concentration has remained the same. Now, this is a pretty straightforward piece of information because there's only two trials that we could use here because there's only two trials where CH3Cl3 is the same, and that's trials 2 and 3. So, all right, so we've kept that constant. And so what did we do to the Cl2 concentration? Well, we doubled it here. So again, we're changing Cl2, leaving CHCl3 the same. So what was the response to the rate? Well, it went from 0.069 to 0.0098 or 0.01. Well, okay. This is a little bit trickier, right? Because if I were to do my calculation, right, and I get 0.0098 divided by 0.0069, what we see is it didn't go up by twice, it didn't stay the same, it didn't quadruple, right? The things that we would expect it to do if it was 0 first or second order. It went up by essentially 1.5 times, or more specifically, if I did it, it went up by 1.42 times. So it didn't double, but it didn't stay the same. So there's no order that we can do just by looking. So it got a little bit trickier here. So let's see what we can do. So the first thing is, we know that CHCO3 is first order, right? Because we can do that by inspection. Now, what we can say here is that Cl doubling, the rate increased by about 50%, right? If it went up to 1.5, right? So if it was times 1.5, that would equal a 50% increase. Now, so that doesn't, we can't really just come up with the order there exactly, you know. So we're going to solve this by math, right? So we could conclude that maybe the order is 0.5, right? Because going up by 50%, that's what it would be. But we don't need to guess, we can do it mathematically. So I want to show you that mathematical process. And there's other examples in the book, and I will also be posting examples from other sources that also have these types of problems in it. So the key is, we're going to take the rate and take these two, the rate laws for these two, and essentially divide them. Now, I've done a little simplification here. So what I've done is I've taken the two trials, trials 2 and 3, and written out the rate law and essentially divided them. So we have the rates. So this is trial 3 here. This is trial 2. So these are the rates, the rate constants, the CHCl2 concentration, right, it's 0.2, or excuse me, the Cl2 concentrations, 0.02 for trial 3, right, 0.01 for trial 2. Now, notice I didn't write, but I could. And so I'm just going to, just to make sure it's clear, I could write the CHCl3 here as 0.02 raised to the n. But it's the same, right? 0.02 raised to the n. So as I go through, so I'm taking this equation here for trial 3 and this equation for trial 2 and dividing them. Now, the reason I chose to do it this way is, why is trial 3 on top? Well, because it has the higher rate, and so it just makes the math a little bit easier, I think. Now, as we go through this, we see that certain things cancel out. So first of all, these cancel out, right? Because the concentration of CHCl3 hasn't changed. So that's why I didn't write it out initially, because it's going to cancel. Also, the rate constants are going to cancel, right? Because the rate constant is constant with concentration. So we reduce down to 0.0098 divided by 0.0069. As we said earlier, that's 1.42. And we have 0.02 divided by 0.01, that's 2, raised to the m still. So we get 1.42 equals 2 to the m. Now, this is where the math becomes maybe a little bit tricky, and that is, how do we figure out what this exponent is? Well, the way that we figure out what a power is we take a log. And so we're going to take the log of both sides, And if we take the log of a power, right, we take the log of the exponent comes down, and we get m times the log of 2. And the log of 1.42 equals 0.152. So in taking the log, we've brought the exponent down so that we can solve for it. So now it's just a pretty simple math problem. Taking 0.152 divided by the log of 2 is going to give you m. Simplify the log of 2, do the division, and we see that m is 0.5. So the order of m is going to be 0.5. So this illustrates a couple things. First of all, we can solve this mathematically, and we could have done the same thing to solve for n, right? Instead of doing it by inspection, we could have done it mathematically and we would have come up with 1. Now, it's just we can save ourselves some time if we can just look at the data and do it by inspection. But if we need to, we can do it mathematically, especially when it's not 0 first or second order and it looks obvious that it's 0 first or second order. So now we've come up with the answer to part A, which is what's the rate law. So the rate equals the rate constant times CHCl3 to the first order times Cl2 to the second order, to the half order. No, again, so orders don't have to be 0, 1, or 2. They just often are. The second part of the problem wants to know, what's K? What's the rate constant? Well, we have two variables here. We have the rate and the rate constant. So in order to solve the rate constant, we need to know the rate. Well, we have built-in rate information. I guess we have 4 rates, in fact, right? We have trial 1, we have a rate, trial 2. So the idea is we can pick any trial. It shouldn't matter which trial you pick. You should get the same rate constant. That's the whole idea, that it's constant. And so we're just going to pick a trial. So I picked trial 3 here. So my rate is 0.0098 meters per second is the units, right? Molarity per second, meters, molarity per second. So rate constant, we plug in whatever our concentrations are. In this case, they were both 0.02, raised to our particular exponents, and then we just solve. Right? Raised to the first order, that's itself, so this is 0.02. If we take 0.02 raised to the half order, we get 0.14142. Simplify this out. We get rate constant times 0.0028 molarity, right? So remember, the units of this are molarity and the units of this are molarity. So our units here are molarity to the 1.5, so not molarity squared, right? Molarity to the 1.5. Now, to get K, of course, we're going to bring this over. So we're going to take our 0.0098 divided by 0.0028284, molarity per second on the top, molarity to the 1.5 on the bottom. So if we do all this out, we get 3.5. Now our units here are a bit crazy because of the half order here. So we get molarity to the minus 0.5 over seconds equals our rate constant. So another way you could write this out would be 3.5, right? Molarity to the negative 1/2 seconds to the minus 1, right? So now remember, rate constants are going to have units that are going to be varied based on what the overall order of the process is. So in the book you have a table that tells you, okay, these are the units for K if it's 0 first or second order overall. But if it's a different order, like 1.5 order, well, it's going to have different units for our K. But regardless, right? We've calculated K. So we came up with the rate constant. Once you know the rate, you came up with the rate law. Once you know the rate law, you can use any experimental trial, plug in the rate, solve for the rate constant. So that's a pretty common initial rates type problem. Sometimes it's going to be really easy to get them by inspection. Sometimes it's going to be you're going to have to do a mathematical approach to solve for the order. So this is the kind of thing that you'll be doing for some problems. You also want to do this in lab when you're solving for the orders there. So I'll give you a little example of how to do that, as well as, again, I'll be posting some additional problems that have more examples of this. All right. So initial rates laws.